Okay, so working through SkellyCam. Let's see that first part again. Stop all. So SkellyCam, John Fast API branch. It installs through pyproject.toml, and then run entry point is SkellyCam _ main run the whatever. And so then basically this runs this run Unicorn server, so which just runs a fast API app, which is made through this. This is like a string to where the factory is to make the app. And when it runs, it gives you this URL here, and it runs on your local host, which is like it's your network card, which is the same way you connect to the internet, but it's not connecting externally, it's connecting locally. And I'm pretty sure Puff Machine might know more about this than I do, so if I say anything wrong, just shout it out. Or judge me in silence and tell me later. Yeah, and so basically this then defines these routes that you can get to. So API, app factory, this is the part that actually makes like the application that is running behind the server. And then these apps are defined if you click on enabled routers. You go into that. These are the routers. And the main one to look at right now. So basically these are nice because you can then, like this little interface is just built automatically by Fast API. It's like a Swagger thing. It uses Open API or something like that. And you can just hit the endpoint, and the server hears it and then gives you a response, and it says hello from SkellyCam backend. And that route you can see right here is just HTTP localhost 803/hello. And if I just go to that URL, it just gives you that same message. And because what happens when I hit the execute and it sends this command is the server hears the request come in. Health check, Control B, and then this is the API call. It's sort of the green means that it's from the API, and it sends back this JSON that just says blah blah blah, and then that's what the response body is what you see there.
Okay.
And so then camera connection router. So this is sort of the main one. There's a detect cameras and startup and blah blah blah. The WebSocket is sort of it's set up kind of, but it's a little broken, so it's not actually working. But the camera connection mostly is, and so that has /connect. Close. And sort of several versions of that. So a get is basically, it's a call that you get that sort of just like give me information. Like you don't send much. I don't know, whatever. This is sort of getting beyond my depth. But the test one is set up that it will attempt to connect to, I think, all available cameras with default settings, and then record just this single number of frames, and then shut down. So it's just a way to kind of test the connection. And then eventually we can also, it doesn't record yet, but it also doesn't display anything yet. But we build around that. So when I hit that one, I can put, I'm going to shut this down and turn it on back on with the debugger on. And then if I go to connect test, see connect test here, the same guy there, and hit it. I forgot to put, wait, no, stop. I forgot to put the debugger, but that's okay. Oh, there you go. So that's right. Cool, do everything. A lot of logs. So it goes through, connects to the cameras. We haven't detected them, so it runs the detect method, which is the same thing that's hit from this place. Detects the cameras, sees them on windows. You can tell the levels here by the color, so trace is like details. Applies a config. And then this is sort of getting... Okay, we don't need you anymore. From the SkellyCam, core, memory, down here, whatever. So we're building like memory buffers in a shared memory system that we're going to put the frames into so they can communicate without having to sort of go through like when you're talking like your network card or pipes or any inter-process communications are very sort of costly and difficult things. So this is just a way to just save the directly save the bytes that come off of the camera and then access them from elsewhere without having to have any additional overhead. So that starts by just you have to like see what size the data is going to be in so you can make enough space for it. And so we put, so the image is going to be, this is 6 megabytes raw, like a raw 1080p image is 6 megabytes, which is, we can compress it, but we want to compress it like outside of the frame capture loop because compression is expensive and takes time. So we want to do that elsewhere. And then this 217 bytes is like data, like the timestamps and the camera ID and just like metadata about what's in there. And so the total buffer size that I just set aside like a gigabyte of memory just for clarity. That's more than more than we would need, but it's an easy number. And this is the name of that shared memory that is the way to connect to it from other places on the thing, but whatever, details. Trace data. And it goes through, waits for the cameras, and then it starts. So the main shtick here is that it's a trigger camera system. So the previous systems, like it would sort of turn on the camera and then start collecting frames in a loop, just like give me a frame, and then sort of emit them. And then other systems would sort of need to grab those frames to sort of, record them and whatnot, which works. But the challenge is that if you have like a bunch of cameras and they're all running in their own loops, then synchronizing them can be difficult. So this is using a system that happens in a lot of like more research cameras and research grade camera systems where you use research like machine learning research types of cameras typically operate through hardware triggers. So you have like a wire that you stick into it and it sends a pulse, and so you can trigger it to send a frame back to you with like a direct pulse of electricity. So you can get super, super high precision, which it's just hard to get with simple software. So I built this system up so it's kind of using the same kind of approach, where the cameras are all run in like a loop, like a multi-camera loop, and then they get triggered with like multi-processing triggers and whatnot. So there's instead of the cameras running in a loop and sending out frames whenever they get a frame, there's this like higher level sort of loop that's sending out triggers to the cameras, and then when the cameras, so you trigger the camera, and then when the cameras trigger listening loop. So the cameras instead of running a frame grabbing loop, they're running a listener loop, and so the camera says get frame, and then before it gets the frame, it like waits in this like really sort of tight while loop that's looping like 10 times per millisecond, which seems very, very fast, and it is fast, and it's like enough that you might notice in the system, but like your computer can run much faster than that. So it's not really eating up that many resources, and it's running in its own independent process. So you're not going to get any blocking, Python global interpreter lock and all that kind of stuff. So it's protected from anything else going on your computer. So here's that trigger. It does this grab, which basically just tells like the camera device to like get the frame from the camera, but it doesn't decode it yet, which is like the part where it actually turns it from like whatever's coming out of the USB into something that you can like look at as an image. And it only returns a Boolean. Like there's no visual image output yet. But after it does that, it waits for it says, okay, I did it. And then it waits for another trigger that says, like the listener guy, like he waits for them to all say, okay, I did the grab. And then once it hears that from all of them, it fires another trigger that says, okay, just realized I can do this. Oh wait, not that. No, yeah. There. Do. Yeah, and then when they hear the retrieve trigger, then they go and they do the actual retrieval step, which this step takes like 1 millisecond. And very, very fast. This step takes like 7 milliseconds for a 1080p video or a 1080p image on a pretty powerful computer. But the point is that by triggering those separately, you can get much tighter time precision between them. And then once it does that, we now have the actual image. So we immediately grab a timestamp as quickly as possible using perf counter ns, which gives us an integer and hypothetically in nanoseconds, which is realistically more precision than you get out of this type of system. But it means that you're not giving like a float with like a floating point imprecise number. It's like an integer. And then you go into this shared memory and you put the frame, doink. And this is like some crazy thing where you've like, in the setup of this, I reserved a buffer, which is just like a very long string of memory addresses basically, and then convert the image with the metadata into a payload of bytes, doing the metadata separately from the image, because the image is basically already in bytes, so you don't have to spend any effort converting that. But the metadata is super tiny, so you can pickle that, and you don't notice that amount of time because it's so small. So doing those things separately also can shave some time. And then this part right here is where you put it into the buffer using like NumPy kind of slicing-ish syntax. And then you increment an index, and then the camera, and then that's the end for the camera. The camera's now done. It just passes along. But there's this other guy in this camera group called the Frame Wrangler, who has his own listener task. And this guy lives at like the higher level, like in the main threads, like outside of the camera triggering threads, and it's just running this sort of like more. It's like an asynchronous task, and where are you? Yeah, so it runs this async loop, which is not as protected and not as fast as a multiprocess, but that's fine because it's at the top level, and it can sort of run this more like lazy sort of listener that, it asks the shared memory manager whether or not there's a new multi-frame payload available, which just basically asks all the camera shared memories, like if there's a new thing available, and then if it is, then it goes into this, and it double checks that you still have one there, because you have to be very careful because like nothing is protected, so you're like reading and writing from the same memory, so like you can't have, and it's like synchronously, so if you can have collisions that will just make the program crash. So there's a lot of protection to make sure that doesn't happen. Oh yeah, and then you can separately grab either the next frame or the latest frame. So if the front end is lagging, you don't need to get every frame. You just get the most recent one, and then your frame rate drops, and that's fine. But if you want to record the data to disk, you want to get every single frame, and if it lags, that's okay. So you can do that separately, and that just goes in to this. Yeah, so before I was showing you the put frame, and this one I'll call the retrieve frame, and this is just the opposite as the other part. So instead of putting stuff into that, it just pulls it out of it and then recreates the frame outside of that same process. Does a bunch of logging because I'm trying to keeping track of how fast things run. Actually, yeah, so you get like this. So camera 0 wrote frame 0 to shared memory at index 0, offset 0 bytes, took 5 milliseconds. Checksum is this, which is just literally take the whole buffer and just sum it up, so you get a big number that you can check later to make sure that you got everything right. And then this is all it's been 11 milliseconds since the previous run through. Camera is ready to get the next frame. And then this is the multi-camera saying we're triggering them, and blah, blah, blah. Oh, right. And right, and that's where we are right now, actually. The listener doesn't work. There's something blocked somewhere, which is not surprising at all. But yeah, I was able to get, I think, 7 cameras, 6, 7. I think, after like, I was able to get, I think, up to 5 cameras. Oh, I have the notes right here. Yeah, up to 5 cameras running 30 FPS, 1080p, 0 frame drops, and at full 30 FPS. And then once I added a 6th camera, it jumped up to 40 milliseconds, which is like 25 FPS. And then I ran out of USB ports.
Good.
Yeah.
But the frames, it's like something like first in, first out, something like that on the frame, because if one camera is not responding properly.
Yeah. If
the frames be dropped.
So currently, if one camera stops responding properly, the whole system will just stop. It'll grind to a halt.
Okay.
And so that's like one of the like handling stuff like that is sort of like, we get to that later. But you're right that with this, we just need to have some kind of a process that basically says if one camera doesn't respond within a certain amount of time, we'll skip it and then just have an empty frame for that one.
Okay.
Because right now it's like, it's it would get stuck in the trigger loop. Yeah, it would get stuck here.
So the cameras that are working fine will wait until the frames is used?
No. So that's kind of the beauty of this. I should, if I was drawing this, it would be easier. But the process, this whole process, cannot tell what's happening outside. So the cameras just put the frames into the memory, and then it's the job of the listener loop to pull them out. And so basically the parent sort of multi-camera trigger just says grab a frame, and then the camera grabs the frame and then puts it into that shared memory buffer, and then it just moves on to the next frame. It doesn't check if anyone's looked at it. It just keeps moving on. So, and then the other process on the outside is the one that's sort of like waiting for new frames to be available, and when they're available, it copies them out of the shared memory buffer. But the cameras don't know that the listener exists. They're just putting the frames into the queue. And it's not exactly first in, first out, because we're basically putting them into a buffer at specific locations, and then because the buffer is a finite size, it just kind of loops through the available spots when it's putting frames in, and then keeps track of, oh, I just put a frame. Actually, it says right here, it's like I just put a frame at this index here, so that when the listener comes in, it can check. It checks for new frame is available, which checks if so when the camera writes the image or writes the frame to the buffer, it increments this index that says I just wrote a frame to index number 12 or whatever, and then it moves on. And then the listener comes in and says, it says, first of all, should I look, is there new data available? And that will check if the frame that I'm supposed to read is the same, is the one ahead of the one that was just listening. And if it is, I just skip it. That's the part, that's like, is there a frame available? There's no? Okay, I'll come back. And then if it checks if there's a frame available, it says, a frame was written to index 12, but you have only read up to index 10. So you go grab another one. And so that it uses this like parts of the shared memory buffer to do that communication of I wrote something to frame 12 and I just read from frame 13 or whatever. Actually just realized we don't actually need to put the read flag in there, but it's whatever. But that it's like, this whole thing is set up to share like big images across processes. So we just reserve like one tiny little one little byte of that to also communicate like I just wrote to this number and I just read from that number, so that the same communication happens across the board. But the cameras, theoretically, if the listener gets too far behind the writer, the loop will catch up, and I think I set it up that it will crash or throw. I set up that it's easy to turn it from like a warning or a crash or something like that. I think I set it up to be grumpy, so it would crash, but the buffer is large enough for 256 frames from each camera, so sort of it's I think in the same place of like what happens if one of the camera fails is also the question of like what should you do if there's if the buffer catches up. I think for different applications you might have different. I think at some what we'll want to do is have some kind of a diagnostic that will run a test on your computer and say, okay, you should probably have like your computer can handle a maximum of this many cameras at this resolution or that many cameras at that resolution, and we can base those decisions on these types of diagnostics.
Yeah. Mm-hmm. I have different brand, different model cameras.
Mm-hmm. Yeah.
One is faster, clearly faster than the other.
Oh, really? Yeah, and I think that's something else. It's like you can see little pieces of it. It's not really implemented, but a lot of this is also clearly geared around like getting that kind of diagnostic information like reliably and get so that if someone gets the software, turns it on, it can run a little boot sequence that just like tries to send a bunch of fake images. Just like you can easily make just like a random bunch of numbers that are the same size as an image, and then just kind of send these little like test loops through, and then give a report that says, oh, camera 0 is doing this well, and that camera's doing that well, and you can sort of have a little health check that sort of can help people figure out how to tune their system. Yeah, and then the other part that's exciting is, so basically I got to the point where like the listener wasn't working properly, and I was like, that's when I sort of learned how tests work. So I'm not done yet, but I basically a lot close tabs, close all tabs. So the way I'm thinking about it is like there's a lot of like models in the software, like the camera config, which has IDs and resolutions and and it sort of like has certain ways that it should be, and so the pattern I'm going with now with the testing is like every sort of significant part of the data model can have its own set of tests that you can run and just test all these things. And the basic structure of how a test works is like the machine was talking to me about this. I was asking like the AI about it, and it's like arrange, act, assert. So like you arrange everything as it should be, and then you do some action on it. Like in this one, just testing, making a configuration file. So I give it a bunch of numbers, I make a thing, and then I just make a bunch of assert statements that say these are the things that should be true. And then if one of them is false, then it fails and tells you why. And so then basically the way this now can work, and so I did this for the configs, and I also have now done it for that shared memory stuff. So you make a bunch of test images that have a certain shape and size, and then and then you basically run through like a dummy version of that process I said, and just use the main parts of the like the memory model in the way that you're going to use them, and then just make sure that they work. And so I just realized that like it's so dumb because it's such a basic part of software development to write tests, and I just like never learned how to do it because I was raised as a scientist, and scientists don't know how to do that type of stuff, even though they clearly should. And I just realized it's like, so now what I can just do, instead of having to like dig through all this stuff and figure out like, oh, what broke, why did that break, why isn't it making it all the way to the end, if I just make a test for like each part individually and test that each part individually is doing all the things that part should do, then and if the code doesn't work at that point, then it's much easier to diagnose, because you can have confidence that like that there's not some stupid like, oh, you tried to put too big of a thing into too small of a thing, like some uninteresting problem that's actually causing the thing to fail. And it also means that like I can talk to people like Philip, who is very interested in helping out with SkellyCam, but like there's a lot going on here. So rather than saying like, hey, dive into this like complicated thing, I can just say, okay, here's the main parts. This part needs these tests, and we can sort of, Philip can kind of like work on building the tests for the individual components, and have a way to both learn how each part works individually, and also be able to work in a place that's not going to break the functionality of the main software, because he's only building stuff in this tests folder.
Mm-hmm.
So
you think this will come before the new GUI?
Yeah. So
system.
Yeah, so this is also one of the really nice things about this type of a system of making like a back-end server, is that we can kind of decouple the process of development of like the back-end functionality of like, oh, the images and the memory and the blah blah blah, from the front-end functionality that is the actual like the GUI part. So then I have this other very I showed you some, I think I've posted, I don't know if I have, but there's like some other more sophisticated front ends like React and Vue and stuff like that. But the problem of the is that they're complicated. So I just made this super dumb website, sort of, or HTML document that's just like a bunch of buttons, and then this sort of, I say I wrote it, but like this is like me and the machine wrote this code because I don't know how to do this. And it's just like, hey machine, how does shared memory work? Hey machine, like how do I write a website with a button on it? And so how do I make a Tory app so it can make its own standalone? So if I then run, so package.json is like the web dev equivalent of the pyproject.toml, and it defines these scripts. So this is dev runs Tory dev. So that's like, I could push this button in PyCharm, but I'll just show you. If I type npm run dev, it runs this command, and then pops up this simple, ugly app. And that is, first of all, it's a Tory app, so it's like just a browser. So it's the same. Actually, can I do this? Yeah, nice. Sure. And so oh yeah, main.js. Yeah, so this is the index.html, and then down here you just import and run this main.js script here. And then if you recognize these URLs, they are the same ones as here.
All right.
And so basically the buttons, so there's this hello one that we talked about before, and it just, so document is like, actually you can see it here too. This is my Firefox. It's like, whatever, all this stuff. And it gets the button, and then when you click it, it runs this asynchronous function that does a fetch, which is basically calls the route that lives here. That same one there on this port 808,003. Then waits for the response, and then if it hears the response, where are you? Oh, this one. Hi. It gives that. We even have the WebSocket. Technically works. Doesn't. This is it. This red area at a different point in development did display the images from the cameras, but I broke it to make it. It was working, and then I did the shift I mentioned towards the trigger camera method, and then it broke, so that's where I need to fix. But yeah, it's like, where is it? Yeah, if WebSocket, check hi. When it opens, do this. If it, that probably is gonna I don't really. I guess it's fine if it's already connected. I don't know. And then when it gets a message, it sort of tries to pull the JPEGs out, and there's like another part that converts the multi-frame payload into a front-end payload. So that part actually compresses the raw images into JPEGs, and then that's like an easy thing to send over this socket connection and grab them and decode them and turn them into canvases and blah 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 blah. So yeah, so like that's kind of I was talking with like Aaron and Philip and Trent the other day, early this week, about like the roadmap and the strategy if we're going to take to basically like the rollout, I guess, of the 2.0 version, and like, you know, making sure we can kind of like maintain the existing GUI, but also kind of start like sunsetting it, I guess is the term, or like you maintain, like, or maybe LTS or something like that. I don't know what the term is. Like, we're going to maintain it and fix bugs and whatnot, but we're not going to spend a lot of development work to like make it better, because we're going to be doing all this work to like, you know, revamp the back end. And in the meantime, like SkellyCam, because it is both like the most like the core, the most complex part of the technology, because it's actually like doing empirical measurements. It's nice to keep it separated from like the part of like the rest of it, which is basically processing images, which, you know, can take longer, and if it crashes, it's no problem. You just do it again. Like, you know, it's sort of a little more safe. So SkellyCam is now acting as kind of like a microcosm where we're going to figure out like the architectures and the workflows and like how to write front end code, and then sort of like at some point start, you know, sort of like being like, okay, there's something people can use now. And then as we figured out with SkellyCam, we'll sort of start applying the lessons learned to like core free mocap. And
you add dark mode?
Yes. Yes. Oh my God, I'm so sorry. It's so bright. There's so many things in there that it's like when I finally started using, like, I learned how to write JavaScript. I'm just like, oh my God, this is so easy. It's so much easier to do dark mode when you're doing it in JavaScript than it is in Python. And also, like, I didn't know what CSS was when I started this, and sort of, yeah, I live my life in dark mode, and every time I open up free mocap, I'm like, no, it burns. Yeah. And also, like, I still remember you had a request a long time ago of having the logs be something that you can turn off or turn down, like quiet them down so they don't say so much. So I added more logs, but they're more easy. Like, with the lessons learned from the 1.0, we can now go into the 2.0 and make sure that when we set up our logging, that it's set up that you can, you know, there's like a proper settings system that can keep, like, on the front end, you can say which level you want to see. And just basically, yeah, like, and then something will just trigger this to do what it's, just change that value, and then and we can have all of the logs going into the log file, and then just like whatever you, the user, want to see will come into the front end.
Good.
Yeah. So that's my presentation.
I know. A lot of work.
Yeah, a little bit. It's been fun though. It's like it's been kind of, you know, with like classes and stuff like that, and then like I personally have been spending like almost all of my development time in SkellyCam, and like Philip and Aaron have been really holding it down in free mocap land, but like it's like I'm excited to start like merging the streams again. That's kind of the theme, and you know, once this kind of architecture, like, you know, proper APIs and WebSockets and front end, back end separations and make it into main free mocap, just a lot of things will just improve, and and like a lot of old problems will just they'll just go away. They'll be obviated.
Yeah.
And won't that be fun?
Mm-hmm.
Oh, it's 12. I have to run soon, but hi, Ch. Nice to see you.
Hello.
How are you?
I was really curious.